I greet you, dear viewers. Today we are going to look at a topic that is linear algebra and calculus. So we are going to go through the entire topic and see how we can solve questions under this topic. And I hope everyone is attentive and ready to move on together, because I don't want to leave anyone behind. So let's try to follow. Let's try to be together step by step. So in our today's topic, we are going to look at calculus majorly, and when we talk about calculus, we majorly find that we are going to deal with differentiation and then integration. So to begin with, we shall begin with differentiation. Differentiation, that is the usual dy dx. So we find that with differentiation we have some rules that you have to follow. So we find that a derivative of a differentiation is known as, when you differentiate, the result is known as a derivative, and a derivative of a function is denoted as dy dx. dy dx, I hope you are following as I'm highlighting. So in the y represents a dependent variable, and then x represents an independent variable. X represents an independent variable. So differentiation establishes a slope of any particular function. So the derivative of any function results into slope. Consider a function y equals to mx plus c. So you find that when you differentiate, we normally end up with m, which m we consider to be the gradient or the slope of that function. End up with m, which we call a gradient or the slope of a function. So before we start looking at practical questions, we are going to try and go through the rules that we can follow to understand best how we can differentiate functions, or how we can differentiate the variables that we are given. So we have about 6 to 7 rules that we can dwell on for us to understand how we can differentiate an expression. So the first rule is the first rule is the basic rule. So you find that whenever you differentiate a derivative, what we do, we multiply what we want to differentiate by the power, and then reduce the power by 1. We must multiply that expression by the power and then reduce the power by 1. And what we get as a result is what we call a derivative. For example, under the basic rule, we are told that if a function y equals to x power n, where n is the what? Where n is the power and x is the expression or the function. The derivative would be given as dy dx equals to n times x power n minus 1. As we said, we multiply the expression by the power and then reduce the power by 1. Multiply the expression by the power, then reduce the power by 1. So you have an example that says differentiate x power 4. Differentiate x power 4. So let's see how can we differentiate x power 4. Differentiate x differentiate y equals x power 4. So in this case, the derivative will be denoted as dy dx. Why? Because we are differentiating y, the function y, in respect to x. So our derivative would be given as dy dx. dy dx equaling to, so as we said, if 4 is our power, we multiply the expression by the power, so implying that we'd have 4, which is the power 4 times x times x, and then reduce the power by 1. So the result would be dy dx would be 4x power 3. Power 3. Why? Because 4 minus 1, the power of 4 reduced by 1, you get a 3. And this is how would result come up with a derivative if you happen to differentiate x power 4. The derivative would be dy dx would be 4x cubed. That is how we deal with derivatives using the basic rule. So you find that the further we go, these rules keep on considered or inserted into other rules, so meaning it is an addition to other rules we are going to follow how to go looking at. So that is the basic rule. If you go back to the second rule, the second rule is functions with coefficients. So we find that whenever we have an expression with a coefficient, for example, if we have a function of y equals to kx power n, with k being the coefficient, then how do we find the derivative? So we find that the procedure doesn't divert away too much from the basic rule. So still the basic principle applies, whereby we do multiply the expression inclusive of the coefficient by the power, and then reduce the power by 1, as you can observe in this illustration. So for example, if we have y equals to kx power n, the derivative would be n kx, meaning that getting n kx, the kx was multiplied by the power of n, and thereafter the power being reduced by 1. So that is how we can differentiate an expression having a coefficient. For example, we have an example that we can look at. So let's look at this example. So you have functions with coefficients. So the example says differentiate y equals to x power 8x power 4, 8x power 4, where 8 happens to be our coefficient. So how would we arrive at the derivative of such an expression? As we said previously, that when we are differentiating y with respect to x, our derivative would be denoted as dy dxy, because we are differentiating y with respect to x. So in this case, our dy dx would be 4, which is the power, multiplied by 8x to the power of 4. and then reduce the power by 1, as we can observe. Meaning that this would result into 4 times 8x gives us 32x power 3, because if we reduce 4 by 1 we get 3, and that would be the derivative. So our derivative would be 32x power 3, because when you multiply 4 by 8x we get 32x, and then if we reduce the power by 1 we get 4 minus 1, which becomes 3, and that is how we can differentiate an expression having a coefficient. So you observe that we are following the first rule, nothing much has changed, and the very basic rule is the one we are applying to this second rule where we have coefficients. So nothing doesn't divert too much away from the basic rule. That is why I said at the beginning that all these rules are linked or are connected. We need to know all the rules to be able to make the differentiation or to find the derivative of the function. So let's continue. We go to rule number 3. Rule number 3. Rule number 3. So this is where we have functions with constants. Functions with constants. So we find that whenever we differentiate an expression having a constant, normally that constant disappears. When we differentiate a constant, we get a 0. So it happens to disappear whenever we differentiate a constant, as we are going to observe. So as we follow, if y equals to x power n plus c, where c is a constant, then the derivative is given as dy dx equals to n x power n minus 1. So you realize that when we differentiate x power n, we get nx power n minus 1. That is from the first rules we've looked at. And then plus a 0, meaning if we differentiate the c, which is a constant, we get a 0. A constant can be any value, 1000, 1, 1,000,000, 50, so long as it is not attached to any unknown like x. If it is a standalone figure, then we consider that to be a constant, and therefore whenever we differentiate a constant we get a 0. So in other words, it disappears away. So as you can observe a note, we have a note here that says constants disappear on differentiation of functions with constants. In other words, whenever we differentiate a constant, the derivative is always a 0. The derivative is always a 0, as you can observe from that statement. As you can observe from that statement, whenever we differentiate a constant, we get a 0. So you have an example that says differentiate y equals to x power 3 plus 8. Now in this case, 8 is a constant. So want to see, if you happen to differentiate an expression having a constant, what would we get as a result? So let's try to look at this. So functions with a constant. Functions with a constant. So our function is y equals to x power 3 plus 8. We'll come back. So We want to differentiate an expression having a constant. So when you differentiate an expression having a constant, 8 being our constant in this case, so the derivative would be dy dx equaling to, if we differentiate x power 3, this is what we get, 3 times x power 3. As we said, multiply the expression by the power and then reduce the power by 1. Then plus, if we differentiate 8, we get a 0. So we get plus a 0. So why? Because whenever we differentiate a constant, for this example 8 is a constant, we get a 0, or the constant disappears. Take note of that. The constant disappears. So in other words, our derivative would be as follows. It would be 3x power 2 power 2, and that would be the derivative whenever we differentiate a function with a constant. So I hope you're following. So we can now get to another rule, rule number 4. Those are 3. Let's look at rule number 4. So where the function is a sum, so we find that if a function is a sum, there is no big difference from the basic rule or from the rules we've looked at previously. Example, if y is equal to x power n plus x power m, then the derivative would be as, so we find that we'll differentiate each variable alone. For example, we'll differentiate x power n alone, and then we add the derivative of x power m alone, and this would end up as dy dx equals to nx power n minus 1. That is, if we differentiate that, we multiply the x by n and then reduce the n by 1, as you can observe. And then if we differentiate x power m, we would have mx power m minus 1 from the first principle, whereby we multiply the expression by the power and then reduce the power by 1. So we have an example here that says differentiate